Welcome back. This is lecture 23 in our lecture series. And today we'll be dealing with the quantization of gauge fields. Right? So the first things we want to discuss is what are gauge fields and where do they come from. This is kind of a quick review. I hope you have seen this before in a classical field theory course. So I'll just give a quick and pretty direct review of what they are. And then we go on to the quantization, which is really the subject I want to cover, right? So I listed here some references where this is done, right? And the first question we want to answer is, or we want to remember, right, is where do gauge fields come from? One way of getting to gauge symmetries is to think like that, right? So we have seen that if this both the scalar or the fermionic field, in the case of the complex scalar field, have a symmetry where I can change the phase of the field, right? This complex phase is undetermined, and my Lagrangians are symmetric under changes of these phases, right? In this case, alpha here is just some constant, some real number, right? And that's a global symmetry of my Lagrangian, of my theory, right? That leads to a conserved charge, right? Which we have argued that once we go into electromagnetism, that would be actually the electric charge in this case, right? But I could ask, right, what if I take a more general condition than these, right? And demand that my Lagrangian be invariant under a local phase transformation. In this case, I'm making alpha a function of position, right? So alpha is now not a constant anymore, it's a function of position. I'm changing the phase of the field in different points of space-time by a different number, right? This is more general than that. That's actually, in that sense, a particular case where alpha of x is the constant function, right? It's easy to see that these things are not invariant anymore, right? In fact, here I wrote for the scalar one should be the complex, right? But these are not invariant anymore because now alpha is a function of x and doesn't go through these derivatives, right? To get to the other side and conceal with the exponential, right? In order to keep these things invariant, what I can do is introduce a new field and a new derivative. So I exchange the derivatives here, right? For the covariant derivative, this one, right? And now there's a new field that transforms as a vector, right? Just by looking at the indexes here, transforms as a vector and has a very particular transformation rule under this symmetry, right? So now, if I have these fields, the scalar and the fermionic one transforming like that, and this new field, which I call the gauge field, transforming like that, you can put all these transformations there and show that now the Lagrangians are invariant under this transformation. And you get these gauge fields, right? This condition fixes a lot of the properties of this gauge field. In particular, you can show that the most naive version of these, you cannot even have a mass for this guy, he has to be massless, right? And it also fixes the form of its kinetic term, which I'll show later. If you want this to be a physical field, you then have to put also a kinetic term, right? Which is kind of fine, and was the version of how people saw gauge fields not a long time ago, maybe 10, 20 years ago. That was the state of the art of this discussion, right? But the problem with it is that it puts too much emphasis on the gauge symmetry, right? Thinking like that, it seems like you postulated a new symmetry for nature, right? And that led to new physics, right? The existence of this field and the properties of this field. And in fact, in many cases, that was how it was done. Particular one is QCD. In the case of QCD, we knew about a global symmetry. It was not a U1, it was a SU3, a more complicated global symmetry. that then people knew there was some force keeping protons and the quarks within protons and neutrons together, and they thought, what if we gauge the SU3, and then you got QCD out of that, right? And that was predicted a lot of the properties of QCD, which were later confirmed, right? But in fact, we know that most of, all of the physical properties of the system are already fixed by the global symmetry, in particular the conserved charges. Right? We also know that you can basically turn any theory into a gauge theory. You can just put some extra degrees of freedom and make any theory into a gauge theory. And that kind of points in the direction that the gauge symmetry is not really something physical, but more of a trick we can use to write proper Lagrangian. And then you can then throw these extra degrees of freedom away and get a physical theory, right? You could think this the other way around, right? How some symmetries in nature are gauged and some aren't, right? For instance, you have baryon number conservation in QC in the standard model that is not, as far as we know, a gauge symmetry. It's not a gauge transformation, right? It's just a global one. Right? So another way of approaching this is to follow the program we have been following, right? Which is to keep looking for representations of the Poincare group, right? We already did this spin 0, then we did the spin half, and now we're doing the spin 1 representation, right? This guy's spin is 1, right? You can just check that from the representation of this guy under the Lorentz group. It's a vector, right? And then, since this is a vector, it has 4 different degrees of freedom, right? A0, A1, A2, and A3, right? And then you go on and try to build a Lagrangian, right? In the process of trying to get a sensible local field, quantum field theory, which you have to demand a lot of things. You want it to be unitary, renormalizable. This is an important one in this discussion, and many other of the properties we have been demanding of these theories. You see that the easiest way of doing that is to, is the way you can actually build the blocks you want is to impose a gauge symmetry for this guy, right? Another way, you don't know renormalization yet, so it's hard to make this discussion at this point. But one way you could think of is that we know that in nature, vector bosons, right, do not have 4 degrees of freedom, right? They either have 2 for massless ones. You know that, right? The photon, it has only 2 polarizations because the electromagnetic field, electromagnetic waves in vacuum only have 2 polarizations, which are transverse to the direction of propagation of those waves, right? And 3 for massive gauge bosons. Right? And the way to eliminate these extra degrees of freedom that you have here from the representation of the Poincare group is to impose gauge symmetry. It works as a constraint that eliminates some degrees of freedoms, and then you get the physical states, right? Anyway, either following this kind of old-fashioned logic or the most popular ones nowadays, right? You get to fields that transform in this way, right? That's how the field must transform, right? You can do that for the U1 symmetry, right? Which is a simple phase change, local phase change. But you could do that also for more complicated ones, right? For non-abelian, for transformations that belong to some non-abelian Lie group, and which, by the way, acts only on the fields, right? These are not space-time transformations, right? I'm changing the form of the field, in this case, the phase of the field, right? Of the scalar or the fermion field, right? And the same is true here. And that's how QCD works. QCD falls in this category. Same for the SU2 left, I mean the electroweak theory, right? And just to give some names here, when you do that, of course, when I exchange this derivative, say, by this, right, I'll have a term here that is psi bar A mu psi. So I have an interaction between psi and this new field A, right? And that interaction will be controlled by this constant. Same thing for the non-abelian case. So these guys become coupling constants of my theory. So there, when you go from the global symmetry to the local one, you get interaction, right, between the gauge fields and the scalars or fermions, right? These interactions are, by the way, very constrained by the global symmetry, right? So a lot of the properties of the gauge interactions is fixed by these symmetries, right? And these are the structure constants for the case of the non-abelian group, which carry all the algebra, right? Knowing these numbers is equivalent to knowing all the algebra of this symmetry. And these little indexes are running over the number of generators of my non-abelian Lie group, which means these fields will transform under the adjoint representation of the group, which is another important fact for gauge fields. They will transform under the adjoint representation of the symmetry of the group of transformations that you're building the symmetry for, right? So now we want to quantize these guys. Essentially, I'm looking at spin 1 fields, and the only sensible spin 1 theories I can build are these gauge theories, right? Are these gauge fields. Let's start with the abelian case, and later we can generalize to the non-abelian one, right? Since these guys have spin 1, they will be bosons and follow the same kind of commutation relations we had for the scalar, right? So let's use the quantization of the scalar field as a template for what we're doing here, and we'll see if any subtleties arise, right? So we want to do the same thing we did for the scalar, which was to define a functional generator, which was given, let me keep a normalization here, by the path integral of the exponential of the action, right? D for x Lagrangian plus the source term. Now I don't want to put the scalar product because I'm keeping it inside the integral, right? And we rewrote this for the free theory as this thing, right? Just specifying the Lagrangian. For the free theory, we could do some integration by parts here and rewrite this guy as a quadratic term on the fields with the Klein-Gordon operator right here. Phi plus J phi, and minus in this case because I brought a minus outside. Yeah. Fine, and then this integration for the free theory I can do because this is a Gaussian, right? And I got this exponential of minus half of d for x, d for y, j propagator j, right? And that's pretty much it for the quantization of the free theory, because now I can get green functions out of this just by doing functional derivatives on the generating functional and connecting points by this propagator, right? And then I'll go for the interacting theory by inserting the interaction perturbatively. So that's the idea. I want to replicate this idea for the gauge field now. So the first thing is to think about a Lagrangian. I want a Lagrangian. There is Lorentz invariant, so all the Lorentz index must be contracted, but it's also invariant under this gauge symmetry, right? Well, this one. So the field transforms in this way, and I want it to be invariant under that. Right? One form of the Lagrangian that satisfies both of these conditions is this one. It's not the most general one, right? But it's sufficient to see the problems I want to show. Right? This is writing explicitly for those that don't remember what F mu is del mu A nu minus del nu A nu. Right? So this is F mu, and I have it again here, del mu A nu minus del nu A nu. I hope you have seen this before, right? And know that this leads to the Maxwell equations for a electromagnetic field in the absence of charges, sources, right? In particular, I'm saying this is not the most general form, but I want you to keep in mind that in particular, a mass term like this is not allowed, right? This is invariant under Lorentz, but is not invariant under gauge transformation. So this term I cannot write, right? So keep that in mind. Now I want to plug this in an expression that looks like that one, right? So I want to write now a z of j, which is some normalization, an integral over this vector field, now that I'm quantizing it, right? So I have a path integral in that field, and the action, right? d for x of the Lagrangian plus, and now you see, I need a source for this field, right? But since this guy is a vector, the source needs to be a vector too, otherwise this term will not be Lorentz invariant, right? And this break gauge is symmetry, but we'll see about that later. For now, think of J just as a fictitious source, so in the end I'll take it to 0. Right? And this object, right, I want to plug F mu here and write it in this way. So I want to actually write a quadratic form for the A nu here. Right? That can be done. First, I'll notice that this Lagrangian can be written as just doing the distributive here, minus 1/4 of, let's do this distributive, so del mu A nu times del mu A nu, right, minus this guy times this one, minus this guy times this one, and finally minus minus plus this guy times this one, right? So this one, let me get some colors here, this and this are the same, right? Just have to rename the Lorentz indexes, and same for these two, right? They are exactly the same thing, right? Just renaming Lorentz indexes. So I'll get a factor 2. I have two terms with a minus relative sign, and there's a factor 2 here that I can see with this 1/4. But I also want to put all the derivatives in the middle, right? So I have to do some integration by parts. I have two types of terms there. One is this, right? d for x del mu A nu del mu A nu, right? The yellow one here. And these I can rewrite, it's d for x del mu times A nu del mu A nu minus d for x A nu del mu A nu. So both derivatives are acting on this guy now. All right, this part I can throw away with the proper boundary conditions. Eventually we can do this in the Euclidean space and that proper boundary condition we know will be cyclic boundary condition, so periodic boundary condition, so that goes to 0. So that's what I have, and I want to rewrite this just to make it really explicit. Let me raise this index here, right, and contract those two, right? So that's minus d for x g mu a mu. So this is this part. I'm using mu, but let's pretend I change to alpha first here, right? And I'll write this contraction of the alphas as this operator a mu. All right, so that's the expression I want for this guy. Notice the minus sign here, and I got g mu here, which is kind of small because I was running out of space, right? And now for the red terms here, I'll have d for x, del nu a mu, right? Let's take this one for instance. Del nu a mu, del nu a mu. Right? Again, integration by parts. D for x, del nu a mu, del mu a mu. This will go to 0 by boundary conditions eventually. D for x a mu, del nu del mu a mu. Right? And there's this minus sign here. Just I want this to be like that, right? Just to be easier to group with this one, right? Remember, these two guys had a relative minus sign, right? And I got a factor 2 to conceal this 1/4 out here a little bit. So what I got is the Lagrangian of half. This minus here I used to conceal these two minuses over here, and I got a mu g mu operator del nu del mu a mu. And that's the convenient form for this Lagrangian, right? Because now I know that I can plug this back in here and do a Gaussian integral, right? And do a Gaussian integral and see if I can invert this operator, right? By the way, if I do a classical, if I do look for the classical equations of motion, as I said before, right, for this field, right, I'll get this one, del nu acting on a mu, which are Maxwell equations in covariant form, right? Which is great. Now I know what field I'm talking about, right? This is the photon, right? If I quantize this thing, I'll call the particle photons because I'm quantizing the electromagnetic field. In fact, you might have recognized the interaction. If you explicitly write the interaction with this guy, with the fermions, using that form for the covariant derivative, you'll see that's the minimal substitution you do to couple electrons to the magnetic field, electromagnetic field, right? So that's who I'm talking about here, right? So let's proceed to the quantization, right? I want this operator to be, I want the inverse of this operator, but there's a problem here. And now the trouble starts, right? Because I'm summing, right? When I'm doing a path integral, I'm summing over all the forms this field could take, right? And there's one particular form that can be problematic, which is this one. This is what we call the pure gauge configuration, right? And why is this problematic? Because let's act with this operator here. Minus del nu del mu, acting on this a mu, right? I'm using the classical equation, of motion, right? This is, I just have to start contracting. Oops, this needs to be a mu here, right? I'm acting this on a mu, right? And if I contract the indexes here, what I get is this, right? The derivatives commute in here, so this is 0, right? So now I found eigenvector with eigenvalue 0 for this operator, right? We know this story from before. You might suspect the boundary conditions, but that's not the problem, right? In fact, I have now an infinite amount of configurations that are just like that. There's one for every function. And that, of course, shows up in the propagators too. Let me show you, right? What this is doing is that when I do the path integral, right? When I go and try to calculate this path integral, right? I'll be summing over I over 2 d for x of this thing, right? And every time I choose a configuration which satisfies this condition, this is 0. That means the exponential is 1. And I'm summing over these 1s. So my integral is diverging. And not in a multiplicative way, right? Or not obviously in a multiplicative way, right? I'm summing over a lot of these configurations. What happens to the propagator? You see that even if I postulate an inverse to that operator, right? So G mu, the box operator minus del nu acting on del nu lambda x y, which is delta lambda mu Dirac delta, right? This is, you know, this guy needs 2 indexes because it will be contracted with a mu and a nu on both sides, same way it needs 2 positions, right? So that's the most general thing you could write for it, right? The problem is, if I apply a derivative here, let's suppose I act on both sides of the equation with del mu, just to see the problem, right? On this side, this will become del mu box, right? Del nu actually, box. In here, the box del nu. So again, this is 0, right? Let it be like that for now. Del nu lambda x minus y. And on this side, I just get, again, the derivative will be del lambda acting on whatever all these things are acting, right? This is contracted with something on the right side. The problem is I have a 0 here. Not only this is diverging, I mean, that's normal for green functions, but now this green function is multiplied by 0, which this guy would be, I mean, there's no solution to this, right? You cannot invert an operator that has 0 eigenvalues, right? And this is arising from these pure gauge configurations, right? The thing is, if you think physically, right, the gauge invariance is behind the problem. Because now I'm summing over many configurations of a mu, right? But let's suppose I choose one. Now this is just some configuration of a mu. My path integral will add this in the path integral, but then it will also add this one for some function. We'll also add this one. We'll also add this one. And we know that if my system is invariant under this kind of transformation, which is the gauge transformation for this guy, right? All these fields are physically the same, right? If I take a field and add del mu alpha to it, right? I'm not changing the physical situation because this is a symmetry of my system, right? So not only I'm adding over all the physical configurations of the field, I'm also adding each of these configurations, these physical configurations, an infinite amount of time, right? I'm summing too much because of this gauge redundancy of my system, right? I want to identify all these four, in this case, configurations of the field as the same, and I don't want to add them up in my path integral, right? So clearly, I need some way to fix the gauge in my path integral. I want the path integral to go over all the different configurations of the field, not the same configuration again and again. Before we go to the path integral, let's take a look at the classical solutions for this field and see how the gauge fixing influences those classical solutions. So as I said already, the classical equation of motion is just this, right? The Lambertian of the field minus del mu a mu equal to 0, right? This is exactly this thing written more appropriately, right? And this is in general a bit difficult to solve, right? But there's a gauge fixing condition that we could impose called the covariant gauge condition. Covariant gauge, or also the Lorentz gauge. Pay attention, this is not Lorentz, the guy from the Lorentz transformation. It's another guy. This is Ludwig Lorentz. Probably pronounces the same way, but it's not the same way to write, right? Which is just impose del mu a mu is equal to 0, right? This fixes part, I'll show you later, this fixes part of the gauge redundancy that we have here. And it implies that the equations of motion are now just this, right? Which is Klein-Gordon for a zero mass state, right? Once again, I find something very similar to Klein-Gordon, right? Because of course I'm dealing with relativistic theories. That means also that I know the general form of the solutions, right? Which will be something of the sort of the exponential of plus or minus I k x, right? This is the 4 momentum, 4 position, right? But now k squared is 0 because it's the Klein-Gordon for a zero mass particle. And I need to put something else here to carry over this index, right? Which now I'll call this epsilon mu. And it's plays the same role as the u and the v functions that I had for fermions. It takes care of the spin information, the orientation of angular momenta, the intrinsic angular momenta of this guy, which is a vector now, right? So it needs to be a vector too, right? And will tell me how the spin is oriented, how this guy is polarized, in other words. And of course, those, if I go back to the gauge fixing condition, then I can turn this gauge fixing condition in a condition for the momentum, right? And in fact, for a combination of polarization and momentum, which is the following. Let me write this guy in this way: d for x e to the ipx del mu a mu x. I'm just doing the Fourier transform of this guy, right? This becomes, now let me rewrite A mu in terms of the solutions, right? D for K and K, epsilon, this is some normalization, epsilon mu K, exponential of plus or minus I K X, right? I'm putting both signs here, that way I get conditions for both solutions, right? I'm putting all the solutions here, right? And that means I get, now I can take this derivative going here, that takes down a power of K, right? And then I can integrate on the position and get a Dirac delta, right? So that becomes the 4K over this normalization, K mu epsilon mu of K, right? So this came from this derivative, right? I don't care too much about the signs because it's all equal to 0, right? But the sign is important within the Dirac delta that I made show up here. I'm also not worrying too much about the 2 powers of 2 pi because I have an arbitrary normalization here, right? And I have these 2 signs propagate here, right, between P and K. And that means I can now integrate with both signs, right, and get the condition that for each sign I have a different combination, but the important point is that my polarizations are transverse to the momenta, right? That's the important point I'm getting here, that they are orthogonal, right? The polarization should be orthogonal to the momenta, and I can use that to eliminate already one polarization, right? But that doesn't fix everything. It's easy to see that I still have some freedom fixing the field with the Lorentz condition, right? To see that, imagine the following configuration: some A mu prime, which is equal to some A mu del mu lambda. That's a gauge transformation, right? But now imagine lambda satisfies this condition. That means that both of these guys satisfy the Lorentz condition, right? If one of them satisfy that this is 0, the other one will satisfy it too, right? Even if they are different by a lambda, right? I just have to act with these derivatives here, and you see if lambda satisfies this condition, then both will satisfy the Lorentz condition. And that means I still have some freedom. I still can change. My gauge is not totally fixed, right? The way to fix it, right, we could improve our gauge fixing condition by additionally, right? I keep this condition true, right? But I add a second condition, which is, let me show you this. So I'll put now another one, which is that A0 is equal to 0. Which now combine, right, to give me this condition. So I have essentially that one becomes this one. I can just substitute that condition by this one, and I have this at the same time, right? This is called the radiation gauge or the Coulomb gauge, which I think you probably saw before, right? And the only restriction here is that this is a good gauge, especially this part, right? It's a good gauge fixing condition for the vacuum, right? Otherwise, if I have sources, remember, then these will be different from zero, right? If I have charges. But if I'm thinking about just the electromagnetic field, this is fine, right? That implies, of course, that epsilon, the zero component of epsilon in that general solution I wrote before, is zero, right? Because I don't have A0. And then, of course, this orthogonality condition right here will become just this, which is very familiar for people that did classical electrodynamics, right? And now I'm just have two polarizations that will satisfy this condition, because this is, I have now three components for the polarization, but that equation allows me to remove the longitudinal one. It needs to be zero, right? And that's why this is also called the physical gauge. And the classical solution in this gauge will be, right, now that I eliminated the time component of the field, I just have the solution written already in terms of my relativistic normalization and all, right? Mind you that I'm summing over just two polarizations because of that condition right there. And I have some coefficients which I'll just name A and A dagger, but remember we're still in the classical theory here. I'm not inputting any commutation relation. It's just a general classical solution, right? In that gauge, right? With the following conditions, which I'll just write explicitly here. So k square is 0 and k scalar epsilon lambda of k is 0, right, for both of these polarizations. So normally what we do with this epsilon, right, we choose two, you have to choose a basis, right, but usually you choose them in a way that is normalized. So we usually make the additional condition, right, so that the two polarization vectors are orthogonal between themselves and normalized. Now let's see how the canonical quantization works in the physical gauge, right? I won't go through all the details in this. I just want to show you the difficulties that will start to arise once we try to do canonical quantization for gauge fields, right? This is really where path integrals shine. So I want to go to path integrals as soon as possible. If you are curious, I'm not saying you cannot do it. You can actually do it in the canonical formalism, but it's much better to do in path integrals. But if you're curious, you can, in the case of the physical gauge, that's the reference I think you should take a look at. Let's see. So first, I want to impose the gauge fixing condition for things that now will become operators, right? So now I cannot just put a condition like that, right? Because A is an operator now. So what I have to do is to impose a set of conditions that basically imposes this to everywhere where the operator A could show up, right? For instance, I have to write something like that, right? So the expectation value of A in any state should be 0. And also the commutator of A with other operators in my theory, right? In this case, a vector. I put a hat on top of the vector here, right? Should also be 0. Right? That will impose this gauge fixing condition at the operator level. Right? I have to define a conjugate momenta, right? Which in this case you can check and see that this will be F0I of that F mean u, right? Which means it's the conjugate momenta will be the electric field, right? And then naively, right, assuming I managed to impose these conditions, define the conjugation momenta, the naive thing to do would be to impose commutation relations, right? Just take the Poisson brackets of my theory and turn them into a commutator of x prime. Again, I'm doing the same I did for the scalar field. I'm using equal time commutation relations, and I have I here because I only have the vector part of A, right? A0, 0. That I can write as, let me put it like that, you'll see why pretty soon. d3k 2 pi cube delta ij exponential, I forgot, put a j here, exponential of I k x minus x prime, which is the usual thing, right? The Dirac delta of x minus x prime. You'll see in a second why I want to write this as a Fourier transform of the Dirac delta, right? The problem with this relation is that it does not satisfy the conditions I want, right? Let's suppose I apply, right, these derivatives on x, right, not x prime, and apply that to that commutator, right? What I'll get is, let me copy the commutator here. This will be equal to I del xi of this thing, which is minus d3k 2 pi cube kj exponential of I k x minus x prime, right? Which is not 0 by any stretch of the imagination, right? So I'm not satisfying this condition already, right? Just using the electric field of as the operator here, right? The lesson to be learned here is that now I'm dealing with a theory with constraints, right? These two are constraints, and this prescription for quantization that I have, that's not based on any deep physical theories, right, or axioms. I mean, this prescription for quantization does not work in the presence of constraints, right? In fact, Dirac has a very good series of lectures on this, which you can find the notes. I think the reference is on section 15 of Nastasi's book, where he goes deeply into how you classify constraints and how you include them in your quantization prescription. But for now, it suffices, right, for us here, it suffices to notice that I can change this part, right? Take this as the quantization prescription, but instead of using a delta ij here that leads me to the usual thing, I can replace that delta ij by another delta ij, which is this delta ij minus ki kj over k squared. If I do that, now my commutation relation becomes, I take this thing and instead of imposing the usual one, I impose this, right? I d3k over 2 pi cube, this thing, exponential of I k x minus x prime, and this I can rewrite because I can, I can substitute these ki and kj's here by derivatives acting on x, right? Because then I'll get powers of k, right? So I can substitute these by derivatives and take them out and rewrite this as I delta ij minus del I del j. Same thing here, right? I just exchanging the k's by derivatives. Of course, this is an operator, so I'm thinking about the inverse operator that does that, right? And these all acts on the Dirac delta, right? Because once I remove this from the integral, I have the Dirac delta again. Right? And with that prescription, right, if I go back and calculate this, A electric field 0, right? This now is 0 because the derivative will go inside here, take down a power of k, right? Ki, this will be a del I, right? That will go down and take down a power of ki. And then this ki contracted with this thing, right? Delta ij, think at this level, right? The derivative goes on, act on x, takes down a power of ki. This is just substituting here kj minus ki times ki kj. Now it doesn't matter really where the indexes are because this is all Euclidean, but I'll have k squared here and this is 0, right? So now with that different prescription for quantization, I can actually get my condition satisfied, but I had to modify my quantization, right? Which is inconvenient at last, right? If I substitute these commutation relations back into the definition of the general solution for A, so if I go back here, right, substitute this guy into the commutation relations that now I have, right, these ones, then I see that I get the same for A and A dagger. So it's still true, happily, that A and A lambda prime dagger of K prime will satisfy the following condition, which give us hope that all the creation and annihilation stories will still hold, right? Which is very convenient. And that it is also true that A is equal to A dagger, which is 0, and that comes from the fact that also I'm imposing, right, that A is equal to electric field is equal to 0. Huh? And then if you go and go back to the Hamiltonian, and write it in terms of these commutation relations, or in terms of this A and A dagger, your Hamiltonian will be just half of, this is just result you already know, right? I can write it in terms of electric field and magnetic field, right? But if I go and just write in terms of A and A dagger, this will be the sum over polarizations, an integral over K, K0 over 2 times A lambda dagger of K, A lambda of K plus the other way around, which is exactly the same you obtain for the scalar field, right? With the exception that now you have this sum over the two polarizations, because lambda can be 1 or 2, right? And then if you normal order this, right, you know this is not the normal ordering. If you take the normal ordering, then it becomes, right, the sum over lambda, the integral of d3k over 2 pi cube, k0, which is the energy of one photon, right, times the number of operator that counts the number of photons for a particular momenta, right, for a particular frequency and for a particular polarization. And you're summing over the two polarizations and integrating over all possible frequencies, right? Which is exactly what you expect for a free theory of photons, right? This is just a free theory of photons. So you found a prescription on how to quantize, right? This prescription is uncomfortable for two reasons mainly. One, you had to change you start feeling like you don't know how to quantize theories, right? Because you had to change your quantization prescription, right? Now, that can be fixed to a degree by this Dirac method of quantizing theories with constraints, right? But that's a complicated procedure. But more importantly, this gauge fixing gave you only the physical states, but it came with the price that you destroy the Lorentz invariance, right? I mean, the theory itself is still Lorentz invariant, but now your formulas are not, right? You made A0 equal to 0. That means that going to other reference frames will be difficult. You'll see that eventually we'll make loop corrections. We put interactions here and put loop corrections. That's very hard to do and to keep sure you still have a Lorentz invariant theory term by term in this perturbative expansion if you don't have a explicit Lorentz invariance on your expressions, right? You're choosing a reference frame in a way. So that's very inconvenient, right? So maybe it would be better to pay the price of having unphysical polarizations in your theory, right? Keep those unphysical polarizations around, but keep Lorentz invariance explicitly. And that leads us to the canonical quantization in the covariant gauge, right? Which means I'll be only using this condition, which is explicitly Lorentz invariant. Again, I won't do this in too much detail because I prefer to use our time in the path integral quantization. So if you're interested in the details, please take a look at this reference. I'm following it quite closely, right? In this case, I don't have that condition that A0 is 0, right? So the classical solution, so this is not true anymore. So this classical solution will now include more polarizations, right? I have a d3k, 2 pi cube, the usual normalization, right? And a sum over polarizations. They go now from 0 to 3, right? So there's 4 components here of this epsilon, right? And then the usual thing, which I'll need to quantize. So this is the classical solution for now. X plus A lambda dagger K exponential I K X, right? Which now is only constrained by this, so K square is equal to 0, right? And then usually we choose a reference frame that points in Z in the direction of the momentum, right? Which makes K mu equal to K 0, 0, K. And then I also have to choose a basis for the polarization, which is epsilon mu 0, right? That's the simplest thing you could think. Right? Epsilon mu 1 is just this. Epsilon mu 2 is just this one. And epsilon mu 3 is just this one, right? Which we can indicate, right? One way to indicate this is epsilon mu. Component lambda is the lambda epsilon mu vector is just delta mu lambda. But be careful with this notation because strictly speaking, this is not a Lorentz index. We can quickly see that some of these polarizations, 1 and 2, are actually orthogonal to the momenta, right? So for epsilon 1 and epsilon 2, this is true, right? And those are physical. So those are the polarizations that should be in my theory, right? But 2 of them are not, right? So 0 and 3 actually don't satisfy this condition. They are actually equal to the energy, right? And these are unphysical polarizations. They are time polarization, is longitudinal polarization, and one that points in the direction of time, right? This one is longitudinal to momentum, and this one points in the direction of time, right? And that means that somehow when we enforce this condition, that the physical condition in terms of observables, right, these modes need to cancel each other. Otherwise what we're making makes no sense, right? And now we just have to decide how to implement this in terms of a quantized theory. This is the classical one, right? And we need to decide how to implement those constraints in the quantum one. We will use a different trick than what we used in the case of the physical gauge, right? We will exchange, essentially, we will exchange now this very strong condition, right, that we were trying to impose before, and we had to modify our quantization procedure to do it, right? But now with a weaker condition, right, which is imposed only on the annihilation part of the field, right? So remember, this is that notation where plus means annihilation. We did it for the scalar, right? And minus means creation, right? So I'm taking the annihilation part of the operator and saying that if I apply that to a state in my theory, that's 0, right? So I'm saying now that this is 0 applied to states, right? This is a condition known as the Gupta-Bleuler condition, and we'll soon see that this is really a condition that restricts the states that can be in my theory, right? Just to be definite, let me write A plus here. So A plus mu of x is this, right? Again, I'm just repeating same notation I used in the scalar field before. Sum over lambda from 0 to 3. K A lambda K exponential of minus I K X, right? And of course this condition also implies some other conditions, right? So if I take the Hermitian conjugate, that thing will become, that condition will become a condition on the creation part acting to the left on states. So this will be 0 too, right? Where the A minus, of course, is proportional to, so the A minus is basically the same as above, but instead of A, I have A lambda of K dagger exponential of plus AI KX, right? It's a very similar thing, but involves the creation part. And of course, it's also true that this which is equal to the sum of these two parts is 0, right? Because this is just del mu A plus del mu A minus, and of course one is 0 to the right, the other one is 0 to the left, so the whole thing is 0. So I mean, I'm saying that this is 0, as this is one of the conditions I had before. The only one I'm weakening is this one, the commutation one, right? Is now not necessarily true, so I'm not demanding this, right? Let's see the consequences of that, right? I won't prove, but in this case it works to just use the usual quantization procedure, right? I'm changing my constraints so that now this actually works with one caveat. Let me just write this. G mu delta 3 of x minus x prime. So this will be my quantization condition. Again, the usual thing, right? With just one caveat, which is if you calculate the time part of P0, right? This is, as we know, this, right? And I actually go to the Lagrangian and calculate this. This will be del A, sorry, forgot the dot here, A0 dot, right, of 1/4 of del I A0 minus del 0 AI del I A0 minus del 0 AI, right? Which is just 0, right? There's no A0 dot there, right? So I'm missing the conjugate momenta to A0. Right? In the original Lagrangian, I wrote. So with that Lagrangian, there's no way I can use this quantization, but that's easy to fix. I can put a new term, right, in the Lagrangian. Again, it's a term that I'm allowed to put by gauge invariance, right? So it looks a lot with a gauge fixing term, right? And that does not change the equations of motion of my classical system. So I can do that on the classical level before I quantize. I won't do that in details here. You can look at Matheus, but with that new term, then P0 is well defined, and I can do the quantization. And I'm assuming I already did that. You can go there and take a look at the details. Essentially, you're adding up a term that is 0 by this gauge fixing condition. Right? So you're adding 0 to the classical Lagrangian. Right? Assuming I did that, then I can use the normal commutation relations you see above, right? And write the classical solution and get the commutation relations for A and A dagger, which are these ones. A dagger K prime, which is minus G lambda lambda prime 2 pi cubed delta 3 K minus K prime. Well, which is again what we like it to be, right? This is just the kind of commutation relation that works perfectly for creation and annihilation operators, mostly, right? There's one thing which is odd about this, which is for lambda. Remember, my G min u is plus minus minus minus. So for lambda equal to 1, 2, or 3, this is positive, right? But for lambda equals 0, right, then I have some strange situation that is the following. Let me write it explicitly, right? Dagger K prime, it's the same as minus. This minus can be problematic. Delta 3 of K minus K prime. Right? This minus right here, right, leads to an odd situation because, look, suppose I take the one particle state, just A dagger acting on the vacuum of this theory, right? Forget all the normalizations, they don't matter too much now, right? And let's take the modulus square of this. Right? This is just 0, A dagger 0, which by this relation is minus 0, A dagger A 0, minus the commutator, which is the vacuum. Right? This is 0 and this is 1, right? But that minus came out to be here, and then you have a negative norm state here, right? Doesn't look like a physical state, right? Which is okay. I don't want these states to be physical anyway. Let's see what happens with the Gupta-Bleuler condition now that we know about this, right? Let's think about what happens to this condition under that quantization. Let's write this explicitly, right? This is a sum. There are many things in here, but I'm really just worrying about the sum over lambda from 0 to 3 of K mu, which comes from this derivative, right? We will act on the exponential that is in here, right? And give me this term, K A lambda K psi. This needs to be 0, right? The exponential won't be 0. The rest of the stuff do not matter, right? The important part is this one, right? The derivative drops this K mu, and this needs to be 0, acting on this state. Right? Now let's substitute, right? We know that for lambda equal 1 and lambda equal 2, this is 0, right? It's true that k mu epsilon mu for lambda 1 or 2 is 0, right? That means I can actually remove this sum, right? And just write the two terms that are problematic, the polarization in the direction of time and the longitudinal one. So that's k mu times epsilon mu 0 that's a function of k. This is a0 of k plus the longitudinal polarization, which is k mu epsilon mu 3 k a3 k, all of that acting on this state should be 0. Again, we know this is just the energy. This is just the energy, right? Using those expressions we had before, right? In here we have shown that this is just energy, right? It's K. Which allows us to just divide by the energy and write that A0 K plus A3K acting on psi should be 0. This is, again, remember, I'm rewriting my Gupta-Bleuler condition in terms of A and the annihilation operators now, right? So this should be true for any state in my theory. So it's really, as I said before, a restriction on the states that can be in my theory, right? Let's try to think of a state that actually satisfy these conditions. Let me give you an example. So a state that is created, let's suppose, by A0 dagger of K plus A3 dagger of K, right? This combination acting on the vacuum actually satisfies this condition, because if I substitute that in the equation, right, I'll have A0K plus A3K A0 dagger K plus A3 dagger of K acting on the vacuum. I have to distribute it here. All the cross terms are 0, right? And then end up with the commutators, right? Every time I can put A to the right of A dagger, this is 0, right? And I end up just with A0K commutator with A0 dagger of K plus A3K commutator with A3 dagger K. Zero, and this is supposed to be 0, and it really is 0, because you can see, right, that this guy is minus, because of that minus sign that we had before, 2 pi cube delta of k prime, right? And this is, I could have used different k's here, right? K prime, K prime, K prime, K prime, K prime, K prime, right? And this is plus 2 pi cubed delta of k minus k prime. So you see that sign that is up there, it's important because we'll make it so that really states which are combinations of these two polarizations in equal parts, right, always satisfy the Gupta-Bleuler condition, right? And it's easy to see that any number, right, I could put any power here and you get always the same, right? And the consequence of that is that they will not contribute to observables. Take, for instance, the Hamiltonian, and let's see the expectation value of the Hamiltonian, right? If I write the Hamiltonian for this quantization in terms of A and A dagger, I'll get the following expression, right? So I'm summing over all the four polarizations, 1, 2, 0, 1, 2, and 3. Right? And I have this symbol here that I'll explain in a second. Psi A lambda dagger A lambda, already normal order, right? Of k, of course. These guys are functions of k, right? They depend on k. And this symbol is a result of that commutation relation. So epsilon is -1 for lambda equals 0, and it's positive for the other three, right? That's a consequence of the commutation relation for the time part, for the fact that it has that negative sign in front, right? So if you get the expression for the Hamiltonian, you get a different sign for A0 dagger A0. Now let me simplify the notation a bit, just to make this calculation less cumbersome, right? Let me call A0 dagger of k just 0 dagger, and A3 dagger of k just 3 dagger, right? And A0 of k will be just a 0, and so on and so forth, right? Now, knowing that all physical states of my system have to satisfy these two conditions, right, written in terms of this notation is just that 0 plus 3 acting on all my physical states need to be 0. And at the same time, psi acting on the left, 0 dagger plus 3 dagger acting on the left on psi also need to be 0. I can use a trick here to show the following, right? I can rewrite what is written there for now is just psi, right? Let's focus on the 3 dagger 3 part plus 0 dagger 0, right? That's what I have there. There's also the 1 dagger and the 2 dagger, but those I don't care about right now, right? I can rewrite this, right? I can show that. Take this guy, for instance. 0 dagger plus 3 dagger 0. Right? This is the same as 0 dagger 3 dagger 3, right? Obviously, because they are both 0, right? This is 0 to the left, this is 0 to the left, right? Which again is the same as this 0 dagger 0 plus 3 psi, right? Again, because this is 0 to the right, and which is the same as psi 3 dagger 0 plus 3 psi. This is all different ways of writing 0, right? So let me add them up in a very particular way, right? 0 equals 0 equals 0 equals 0, but I'll add them up like that, right? So psi 0 dagger plus 3 dagger 0 psi plus psi 0 dagger plus 3 dagger 3 psi minus psi 0 dagger 0 plus 3 psi plus psi 3 dagger 0 plus 3 psi. And this needs to be 0 because I just added up a bunch of zeros with the appropriate signs. Appropriate for what? Right? I can show that this, right, now if I put all together and make a distributive here, right, this is the same as 0 dagger 0 plus 3 dagger 3. Right? You have to make all products here, use the signs, all the cross terms will cancel out, and you get this combination, which, by the way, I made a mistake here. The combination that appears here is 3, 3 minus 0, 0, because there's a minus sign coming from psi 0 here, right? So, what that means, what I'm getting here, is that in any physical state of my theory that satisfies the Gupta-Bleuler condition, right, this is 0, right? Which means I can rewrite the energy, right? When I do this sum over all polarizations, the polarization of lambda equal 3 will cancel out the polarization of lambda equals 0, right? So in the end, they don't contribute to energy. Right? They don't contribute to energy at all, and I can actually just write, right? It doesn't matter how I write, the result is the same, but I can rewrite these in this way. Right? So only the physical polarizations are actually contributing to energy. And you can easily see that that's true for any observable that depends on the number of operator, right? If I sum the number of photons over all polarizations, for any observable, say momenta will have a very similar expression to this one, right? And the momenta of the longitudinal polarizations will cancel out the momenta of the time polarizations because they are canceling each other in the number operator, right? And that's true for other observables too. And so the point here, this is a little gimmicky, it may seem contrived, but that's the first example of actually keeping unphysical states, unphysical polarizations in your theory that only cancel each other at the very end of the calculation, right? That's the spirit. The reason we're looking at this is because this is the spirit behind many of the calculations we'll be doing for gauge fields, right? That will be true for the photon field. There will be even more true for the gluon field. We'll be keeping a lot of unphysical stuff around that only goes away at the end by satisfying the conditions for physicality, let's say, right? Which are the constraints, the gauge fixing constraints of my theory, right? So this is as far as I wanted to go with the canonical quantization, and this is it for today's video, right? So next video, we'll now try to do this same thing with path integrals, which we'll do much more carefully and formally. You'll see that's much easier to do in the path integral too. But the advantage of the canonical quantization is that you can see quite clearly where the polarizations are canceling each other, which is kind of hidden sometimes in the path integral formalism, right? So that's it for today. See you next video.